Welcome to the course Geometric Dimensioning and Tolerance presented by LearnCX, which is an initiative by Center for Computational Technologies Private Limited based in Pune, India. Before we start learning, let us first understand the course structure. GD&T course is divided into 5 chapters, beginning with engineering drawing, geometric tolerance, limits and fits, then comes surface finish, and finally welding. As we have a long way to proceed, let's begin with the lectures. First of all, we'll understand what engineering drawing actually means. It is basically a language to communicate between drawings and engineers. Hence, it is stated as engineering drawings are the industry's means of communicating detailed and accurate information on how to fabricate, assemble, troubleshoot, repair, and operate a piece of equipment or a system. It basically explains the meaning of the drawings that has been done on the sheets. It describes the operations that needs to be carried out in order to manufacture the part whose design is drawn on the drawing sheet. Hence we say the ability to read and understand information contained on drawings is essential to perform most engineering related jobs. That is, in general, the complete manufacturing process is first of all documented in drawings. This is the very basic reason why we call engineering drawing as the engineering language. Now proceeding ahead, let us see an example of engineering drawing. So a very generic engineering drawing would contain a title block at the bottom right corner of the sheet. Above it will contain the bill of materials. On the center bottom section you will find the notes which will give some textual explanation of the drawing the sheet contains. As you can see, it also contains a border around the sheet, and last but not the least, you will find the main drawing which would also contain some dimensions and annotations. So this actually completes the engineering drawing. So let us first study the anatomy of a drawing. In general, a drawing can be divided into 5 parts, starting with sheet size. As per ISO standards, sheet size vary from A0 to A8. The sheet size decreases as we go on increasing the number from A0 to A8. Then comes title block. It is an area of the drawing that conveys header type information about the drawing, mainly the name of the drawing, the company name, and various other parameters. The scale contains a ratio between the linear dimension of the image of object drawn and the actual object. As it is obvious that larger objects cannot be drawn true to scale because it will need a very huge size of paper. Hence we have to scale it down in order to fit the object into our paper. Next is field of drawing. It is the main body or the main area of the drawing. And finally, the bill of material. It contains the list of parts used in assembly with its material, its weight and quantity. So going ahead, let's see what are the different sizes of sheets available. So here you can see A0 is the complete sheet. When folded into 2, you will find A1 sizing. Again that A1 when split into 2, you will find A2 sizing. Then comes A3, A4, A5, A6, 7 and 8. One must be familiar with A4 as the standard printing size, and based on that one can understand what would be the size of A0, which is approximately around 16 times the size of A4. Hence it's clear A0 is a huge size. And again, based on the same logic, we can understand what would be the size of A8 paper. Alright, so moving ahead, the metric drawing sizes correspond to international paper sizes. Further refinements were carried out in the second half of the 20th century when photocopying became cheap. The engineering drawings could be easily doubled in size and put on the next largest size of the paper with no waste of space. Which means that if in case you are working on a A2 size paper and you need to scale up the drawing 2 times the size and draw the same on A1, then the same amount of size will be used on A1 too. And to make this achievable, it is obvious that the aspect ratio of all the sheets should be maintained uniformly. So the points to remember now is every other sheet is either half the size or else double the size of its previous one. They also maintain the same aspect ratio. Drawings can be scaled down or up into any size. In older days, the sheets of size A2 and A3 were used widely, but nowadays A4 has become very common since it is the standard sizing of printing devices. Now one last thing which we should not forget is the area of a sheet is doubled when we go up to the next sheet. Now some more details, like all ISO paper sizes have the same aspect ratio 1 to the square root of 2, meaning that the document designed for any given size can be enlarged or reduced to any other size and will fit perfectly. This is exactly what we learned in the last slide. In the right side of the figure, you have the dimensions of various sized sheets. Now we'll see the orientation in the margins. So just have a look at this. We'll understand this by the drawing. The C table actually stands for the top, right and the bottom margin of the sheet, and D stands for the left margin. The major reason why the left margin is larger than the other margins is because the sheets needs to be archived in a folder type of system wherein you will need the left side bit empty, as the sheet holding device like clips or clamps will occupy this place. Rest all is just the same. You will have a border line, you will have a drawing space and a title block at the right bottom section. Now this was for the landscape orientation from A0 to A4, and now let us see the protrusion version specifically for A4 and below sizings. Here you will see the D is same for the left side, the title block is at the right bottom section, you have a drawing space, and here you get larger drawing space in the vertical direction compared to the larger drawing space in the horizontal direction. Next we will understand title block. This is a very generic title block. The title block contains the drawing number, the drawing name, the project name, the company that is preparing this drawing. It also contains the sheet number. This is useful when a drawing is spread out into number of sheets. Then you have scale mentioned here. The date of the drawing is written here. The version of the drawing is written here. Basically, it contains all the non-technical data regarding the drawing. It also contains the general tolerance value. If not mentioned locally, then this tolerance value has to be taken globally for the whole drawing. Then some remarks regarding the machining operations to be carried out can be written down here. The copyright information can be noted down here. Then these columns actually contain the assessment of this drawing. The name of the draftsman who has created this drawing can be written down here. The name of the engineer who checked the drawing must be written here. Same way, if the part mentioned in the drawing is manufactured, then the regarding details can be written down here. The title block of a drawing, usually located on the bottom or lower right hand corner, contains all the information necessary to identify the drawing and to verify its validity. A title block is divided into several areas as studied in the last slide. The title block provides various information such as project details, sheet details, tolerances, scales, manufacturers, and designer details. Moving ahead to scales, all mechanical drawings can be classified into two groups, one when they are drawn to scale and the other not drawn to scale. The basic purpose of having a drawing not drawn to scale is just for presentation purpose. Like say if you are interested in just showing an exploded view of your assembly, then it is not necessary to generate the drawing with a true scale. Other purposes of having a drawing not drawn to scale are like just letting the manufacturer understand the machining processes to be carried out in order to generate the part which is in your drawing. Now the other type of drawings are those which are drawn with scale. Drawings without a scale usually are intended to present only functional information about the component or a system, whereas sheets drawn to scale allow the figures to be rendered accurately and precisely. Moving ahead, designation of scales consists of the word scale followed by the indication of its ratio. Scale 1:1 means that the drawing is of the actual dimension. Now scale x:1, where x is greater than 1, is used for enlargement purposes. Here goes the explanation of it. A very small component can be scaled up or enlarged so that its details can be seen when drawn on paper. The next type is scale 1:x, wherein again x is greater than 1. This is used for reduction purposes. Scaled drawings allow components and systems that are too large for generating its actual size drawings to be reduced into a more convenient and easy to read size. So let us see an example of it. Here we have a scale of 1:24. What it means is the drawings 1 unit of length on the sketch means 24 units on the real part. Half inch equals to 1 feet. It reads like half inch on the drawing equals to 1 foot on the actual component. This is called 1/24 scale. For example, if a component part measures 1.5 inches on the drawing, then the actual component size would be 3 feet. We can understand that from here. Half inch gives us 1 feet on the real object, hence 1.5 inch will give us 3 feet. Now going ahead towards orthographic projections, let us first understand the types of projections available. In most cases, a single view is not sufficient to show all necessary features and several views are used. Types of views included are orthographic projection, auxiliary projection, isometric projection, and oblique projection. Now let's get an introduction of what orthographic projection means. First of all, let me introduce you to the concept of orthographic projection. The orthographic projection will display the object as it will look from the front, right, left, top, bottom or back side, and they are typically positioned relative to each other according to the rules of either first angle or third angle projection. We will get a clear idea of what it exactly means from this figure. On the left side, you have the actual part, and now if you are interested in seeing the part from the top side, the image that will be visible to you is something like this. When it is viewed from the front side, then the image visible will be something like this. Similarly, this is the image that will be visible from the right side. Note that there is a dotted line at this cross section. This dotted line actually means that there is a slot which is not visible when seen from the right side. All the different geometric sections are completely visible from either the top side or the front side. Hence you are not getting any dotted line visible on these two sides. Now let us understand it in a better way. What first angle projection means. In first angle projection, the projectors originate as if radiated from a viewer's eyeballs and shoot through the 3D object to project a 2D image onto the plane behind it. It can be taken analogous to the working of the X-rays. So in first angle projection, the image of the part is projected on a plane behind the part from where it has been viewed. Now talking about third angle projection, the projectors originate as if radiated from the 3D object itself and shoot away from the 3D object to project a 2D image onto the plane in front of it. The very basic difference between these two is the planes on which the projection has been drawn is either behind or else ahead of the part. In third angle projection, you will have the projector planes before the object. Now let us see an example. The left side is the third angle view and the right side is the first angle view of the same part previously studied. Here you can find that when viewed with the third angle projection, the top view will only contain all full lines. Similarly, when viewed from the front, the plane being at the front of the object, you will see all complete dark lines. But when viewed from the right side, the only dotted line that needs to be drawn is for the cut section behind this face of the part. But when this same part is viewed in the first angle projection, then let's not forget that in first angle projection, we have the projection planes behind the part. Hence, when viewed from the top, you will see that this bend in the part will not be visible from the bottom side. Hence, you get this as dotted. When viewed from the side face and keeping the plane, projection plane behind the part, it is obvious that the only face visible to that plane is this back face. Hence, that is the only dark line visible in the orthographic projection. Rest all lines will definitely become dotted as they are not visible from back side. Let us understand the object representations. We have 6 principal views. That is from top, bottom, front, rear, left side and right side. The 6 principal views are created by looking at the object straight on in the directions indicated. So here you have top, bottom, front, rear, right side view and left side view.
Let us see another image that will explain the third angle representation in a better way. Here you can see the observer viewing the object from top. Hence the image is being projected on the top projection plane between the observer and the object. Similarly, if you see it from front or from the right side, the images of the object are projected on the projector planes between you and the object. This is the general convention for third angle representation. So it's a general understanding that the images are projected on some planes which when together connected will form a virtual box, and let us see how this box can be unfolded to get the complete orthographic representation of your part. So here we see the object is present in the center and the projection planes actually form a virtual box around the object, and we have the projector lines released from the part and intersecting the projection planes in order to display the image of the object on those planes. Now the things to notice are the projection planes, the projectors, and one most important thing to be noted is how surfaces A and B are projected. Here we have the surface A and the surface B. A is parallel to the top projection plane and B is inclined to it. So let's watch how it's projected. A is actually projected in its actual dimension, while B's projected dimensions are much smaller than the actual dimension. Similarly, if you see the same on the right hand side projection plane, you will see the B's projection is again having a shorter distance. So this makes clear that all the surfaces are actually projected perpendicular to the planes, and hence all the projection lines, that is the projectors, are drawn perpendicular to the planes on which we need the projection to be displayed. Alright, now let's move ahead. So here what we can see is, if that previous box is unfolded into a single plane, then we will get the 6 principal views on that single plane. Something like this. Here the virtual box is actually unfolded and we got the front view at the center. Then we have the top view. Next is right hand side view. Then the rear view. The left hand side view. And finally the bottom view. So now there's a question coming up. What are the differences between the right side and the left side view? If you can notice clearly, this line is dark here and there we have a dotted line. One good observation is that they are mirror images with one different line type. Similarly, what's the difference between the top and bottom view and the front and rear view? Again, they are mirror images with these differences in the lines. Okay, which view have the least amount of hidden or dashed line? It's obviously the front and the top views. Now let's see the precedence of lines, that is, to create an orthographic view of this part in third angle projection, what needs to be done. So first of all, we are fixing the viewing directions, then draw the visible lines, that is, all the visible lines are drawn. This is in the front view, top view and the side view. Secondly, draw the hidden lines. That is, the hidden lines of the holes are visible. And last, draw the center line. Now, one important thing that I would like to share with you is, when you start to draw an orthographic view, how are you gonna decide the viewing direction? That is, to decide which viewing direction should be the front view and which direction should be the top view, and lastly, which should be the side views. Now if you have some idea about the assembly of the part, then it is pretty sure that you have to maintain the same orientation throughout each and every part. But if in case you do not have any idea of the orientation of the part with its assembly, then in that case we have to decide the viewing direction based on some simple rules, like we should choose the front direction and the top direction in which the least hidden lines are present. That is, we should choose the viewing direction in which most of the features or shapes of the part is visible from that direction. Hence, going back to our main diagram, here you can see the front direction and the top direction are chosen in such a way that the least amount of hidden lines are visible from that zone. That is, most of the features, or rather all the features of the part is clearly visible from those directions. Now moving ahead, let's try to create an orthographic projection. So first of all, we'll draw the visible features of the front view. Here we have the isometric view of the object. Now let's draw the front view. Then draw the projectors of the front view. So we have drawn the vertical projectors as well as the horizontal projectors. Vertical projectors will help us create the top view, while the horizontal projectors will help us create the side view. So you might have noticed that we have not created the hole present on the top surface. Now let's draw the top view. So here we have created the top view with the hole, as the hole was visible from the top view. So what we are making sure is we are drawing only the visible features of the object from each and every view and trying to project back to the front view. So the newly created hole is been projected back to the front view, and hence you get the dotted line on the front view. Now we have to draw a 45-degree projector of the front view. The interesting part of it will be understood now. Draw the right side view. So the horizontal projections coming out from the top view turns by 90 degree from the 45-degree line, and hence gives us the right hand side view, which is created with the intersection of the projectors from the top view as well as from the front view. Now if any new visible feature is present from the right hand side view, then we need to project it back. Now draw the center lines wherever necessary. Hence we have created a complete orthographic view of that part. Now some understanding about the views that we have created. As you can see, the top view and the front view are the adjacent views, and the front view and the right hand side view are the adjacent views as well. The top view and the right hand side view are related views, and more interestingly, the vertical length of the top view and the horizontal length of the right hand side view are equal.
Let us focus into geometric dimensioning now. For dimensioning, we usually use lines, arrows, symbols and text. Let us now see what all we have to study. We'll study the lines used in dimensioning, the types of dimensions, dimensioning symbols, dimensioning space and readability, and finally dimension placement. So let us now focus on the lines used in dimensioning objects. Dimensioning requires the use of dimension lines, extension lines, and the leader line. All these three types of lines are drawn thin with compared to the original part drawing, so that they won't be confusing with each other. Dimension line is a line that terminates by arrowheads, which indicates the direction and extent of a dimension. Ideally, the line is broken at the center and it accommodates the feature value of the feature that it represents. Here in this example, 30 is the feature size, and that is accommodated in between the dimension line, which ends with an arrowhead. Now we'll discuss about other types of lines in the later part. An extension line is a thin solid line that extends from a point on the drawing to which the dimension refers. Here is the extension line in our drawing, where it extends from the drawing with a small gap and it extends till the dimension. It is very necessary to provide this gap to separate the drawing from the dimensions, and as we have already discussed, it should be thinner than the drawing lines. Long extension lines should be avoided. A leader line is a straight but inclined thin solid line leading to a note or dimension value. In this example, all three of these are leader lines. Here in this case, the leader line is represented by an arrow, and in this example the learning process is actually represented using either of these line types. Here the point to notice is it actually starts with an inclination and at the end it is projected straight, where it is connected to the text which it is representing. Now leader lines may be terminated in the following manner: with an arrow if it ends on the outline of an object, like in here it ends at the outline of the part, or else with a dot or nothing if it ends within the outline of an object. Here it is entering the object and hence it is denoted by a dot or else nothing. Now let's talk about something which should be avoided. Like we should not have two crossing leaders. We'll make sure that long leaders are avoided. We should make sure that leaders are not parallel to adjacent dimensions, extensions or section lines. We should also avoid small angles between the leaders and the terminating face. Arrowheads should be drawn between the extension lines if possible. Wherein space is limited, they may be drawn on the outside. Here in this example, these are our dimension lines. We have three types of dimensionings. The first one is the general style, in which the dimension is written within the extension lines, and at the center we have a space provided for the feature value. In this second type, as we are having less space between the extension lines, we have drawn the dimension line completely within the feature and have taken the feature value outside the dimension line using a leader line. Similarly, if the space further reduces and it's not possible to even accommodate the dimension line inside the feature, then it's better to draw the dimension lines outside the features with the arrowheads pointing inside and preferably writing the feature value within the space. Now we will see the types of dimensions. They may be either in the form of linear distances, angles and nodes. The linear distances type of dimensions are usually arranged horizontally or vertically, but at times they may also be aligned with a particular feature of the part. Angles are used to give the angle value between two surfaces or features of a part. Nodes are used to dimension diameters, radii, chamfers, threads and other features that cannot be dimensioned by the other two methods. Now if we revise, our basic purpose for dimensioning is something like to convey all related information to a part with the help of just a drawing sheet, which would not only include the part drawing but will also have some information regarding the part's manufacturing process and rest all details, its length, its scale, non-technical data, technical data, etc. with the help of GD&T, and hence conveying these information would take a lot of space on the drawing sheet if all this data is filled using text. Hence there comes a need to replace the text with symbols. Apart from this issue, there is one more issue of language interpretation which plays an important role if the information is conveyed using text of certain language. As we were talking, the goal of using dimensioning symbols is to eliminate the need for language translation. Now let us understand why it is that important to use symbols. Let's take an example of, say, a product is designed in US, hence the drawing sheet and the GD&T data must have been filled using English language. And if this product is sent to be manufactured and assembled in China, then the Chinese engineer who is going to manufacture the part must understand English language so that he can interpret the information written on the drawing sheet in order to manufacture the part. So there comes a language barrier when text is used for dimensioning. Hence, dimensioning symbols have become standardized globally. Now here we have few examples of the dimensioning symbols, like the diameter is denoted by its respective symbol in the table, and so on. The radius is denoted by capital R, number of times or places is denoted by 4x, and so on. Let us see some more examples of it. Like depth is denoted by depth value. Then if the printed dimension is not to scale, then it should be written with the feature value and an underline. Arc length would be represented as the feature value with a arc on top of it. Symmetry is defined by I, and so on. Now let us talk about some standardization in dimension spacing and readability. Dimensions should be easy to read and minimize the possibility for conflicting interpretations. So it should be crystal clear in interpretation. The spacing between dimension lines should be uniform throughout the drawing. It's a very important aspect. Do not dimension inside an object or have the dimension lines touch the object unless clearness is gained. That is, the lines representing the part should be easily differentiable from the dimensioning lines. Dimension text should be horizontal, which means that it is read from the bottom of the drawing. So this is something to be taken care of. Dimension text should not cross dimension, extension or visible lines. Dimension lines should not cross extension lines or other dimension lines, but still extension lines can cross other extension lines or visible lines. Extension lines and center lines should not connect between views. That is, when you are drawing orthographic views of a part, like say front view, top view and either of the side views, then it should be made sure that extension lines and center lines do not continue from one view to another view. Instead, they should be disconnected between the views. Leader lines should be straight, not curved, and point to the center of the arc or circle at an angle between 30 degree to 60 degree. So this is something to be noted down precisely, 30 degree to 60 degree. Dimensions should not be duplicated or the same information given in two different ways. If a reference dimension is used, the size value is placed within parentheses. So this is something you should make sure that two dimensions of the same feature should not be present in your complete drawing. Now let us see some examples. Like in here we have a drawing which is dimensioned, and I am giving you a hint that there are 5 types of mistakes. Let's see if you can find them all. So I hope you must have found all of the 5 dimension mistakes. Now let's focus on each of them. Here the first one is the spacing, which is not adequately given. Then we have dimensions inside the object which should be avoided. Then the text is overlapping another dimension, hence it should be avoided. Then you have extension line with no visible gap at all from the part. And one last thing, that is the diameter of the hole is missing. You might have also found some other mistakes, like somewhere we have text horizontally written and somewhere vertically, which should also be avoided. Now let us see the correctly dimensioned drawing. Here we see the diameter leader line with the diameter symbol specifying the diameter of the circle. Then all the dimensions that were placed inside the part has been taken out. Gaps has been provided. Text has been turned into horizontal orientation. One thing to note down here is there is no gap visible here because this is not starting from this line. Instead it is starting from the center line, and hence gap is given here, and the extension line is crossing the drawing line, like in here also. So this is a correctly dimensioned drawing. One more thing you should notice here is all the arrows are of the same size. Regardless of the length of the dimension line, you should have the arrows of same size everywhere. Let's go towards the second example. Here I can say that there are 4 types of mistakes. So let us see if you can find all of them. I'll give you some time for that. Now let us see the mistakes. First is the leader line. As we were discussing in our previous slides, the angle of the leader line should be between 30 to 60 degrees. In this example, the leader line falls below 30 degrees angle from the horizontal, so this should be avoided. Here you can see the center line is connected through both the views, which is a mistake. Next is the text. It is not uniform everywhere. Like in all other cases, you have the text in between the dimension line, whereas in this dimension line the text is above the line. Then you have a crossing dimension line with an extension line, which also should be avoided. This could have been avoided by dimensioning this line on the right side of the part instead of the left hand side. Now let us see the correctly dimensioned drawing. Here the leader line has been provided an angle between the optimum range. The center line has been disconnected between the views. The overlapping of dimension line with the extension line has been avoided by shifting the smaller dimension to the right side of the larger one. And finally the text has been included between the dimension lines. Now let us talk about dimension placement. They should be placed in such a way as to enhance the communication of your design, not to confuse them. They should be grouped whenever possible. Dimensions should be placed more often between the views unless it becomes more congested. Dimensions should be attached to the view where the shape is shown best. For example, the diameter of a hole should be dimensioned in that view in which the hole is clearly visible and not the side view of the hole. It is recommended not to dimension the hidden lines. Okay, so that was it for dimensioning. Now we will discuss on a different topic from the same course in the next video. Thank you.